Right now, as you sit watching this video, time is moving differently for different parts of your body. The atoms in your feet are aging slightly slower than the atoms in your head because they reach closer to Earth's gravitational field. Your phone's GPS satellites are racing through time 38 microseconds faster each day than you are. And if engineers didn't constantly correct for this time difference, your navigation would be off by miles within hours. The massive sun above us is slowing down time across the entire solar system, and every step you take up or downstairs moves you through time at slightly different rates. We think of time as universal, unchanging, flowing at the same rate everywhere in the universe, like some cosmic metronome keeping perfect rhythm. We synchronize our clocks, schedule our meetings, and plan our lives assuming that when we say now, everyone everywhere experiences the same moment simultaneously. But this intuitive understanding of time is completely wrong. Time is not universal. It's not constant. It is not even the same for you and the person sitting next to you if one of you is slightly closer to a massive object. Time is elastic, stretchable, and intimately connected to the fabric of space itself in ways that Einstein called the most beautiful discovery in physics, and perhaps the most terrifying when you understand its full implications. What if I told you that every massive object in the universe, from the Earth beneath your feet to the supermassive black holes at the centers of galaxies, is literally stealing time from everything around it? That gravity doesn't just pull on matter and energy, but actually drags time itself, slowing it down in proportion to the strength of the gravitational field. That this isn't some exotic effect that only applies to extreme environments, but a fundamental feature of reality that's operating around you every single second of your existence. The mathematics that describe this time theft are precise and unforgiving. Einstein's general theory of relativity predicts that time passes slower in stronger gravitational fields by an exact amount that can be calculated down to the nanosecond. For every meter you descend toward Earth's center, time slows down by approximately 1.1 parts in 1016, a tiny effect, but one that accumulates across cosmic scales and vast time spans into differences measured in years, centuries, even millennia. But the implications extend far beyond academic physics. This gravitational time dilation means that your future quite literally depends on where you are in the universe. Spend a year near a massive object like a neutron star, and you could return to find that decades have passed on Earth. Live at the bottom of a skyscraper versus the top, and you'll age at measurably different rates. Position yourself strategically in the solar system, and you could potentially live to see cosmic events that would be impossible to witness from Earth's time frame. The experimental evidence for gravitational time dilation comes from the most precise measurements ever made by human beings. Atomic clocks accurate to 1 second in 15 billion years, more precise than any other scientific instrument, have confirmed Einstein's predictions to extraordinary accuracy. These clocks slow down exactly as predicted when moved to higher gravitational potentials, speed up when lifted away from massive objects, and maintain the precise mathematical relationships that general relativity demands. Recent breakthroughs have pushed these measurements to almost incomprehensible precision. In 2022, scientists detected gravitational time dilation by moving atomic clocks just 1 millimeter higher in Earth's gravitational field, a height difference smaller than a grain of rice, creating measurable changes in the flow of time itself. The same effect that Einstein predicted for massive astronomical objects operates at the scale of your desk, your chair, the difference between your feet and your head. But here's where this becomes personally profound. You are not just observing time dilation, you are experiencing it. Every moment of your existence is shaped by the gravitational environment around you. Your biological rhythms, your aging process, your very consciousness operates within time streams that are constantly being modified by every massive object in your vicinity. You don't just live in space. You live in space-time, and that space-time is being continuously warped, stretched, and manipulated by gravity. The cosmic implications are staggering. Near black holes, time slows down so dramatically that what feels like minutes to someone falling toward the event horizon could be years or centuries to distant observers. Entire civilizations could rise and fall, while someone near a massive object experiences what feels like an ordinary day. The universe contains natural time machines where past, present, and future lose their ordinary meanings, and temporal travel becomes not just possible, but inevitable. Tonight, we're going to explore how this fundamental flexibility of time operates at every scale, from the quantum to the cosmic. You'll discover why GPS satellites age faster than you do, how scientists have created time machines using nothing but gravity and atomic clocks, and why the time you're experiencing right now is unique to your exact position in the gravitational field of Earth, the solar system, and the galaxy. We all journey from the everyday time dilation happening in your living room through the extreme time environments near neutron stars and black holes to the mind-bending possibility that consciousness itself might be fundamentally connected to the flow of time in ways that make your awareness dependent on your gravitational environment. You'll understand why some physicists believe that manipulating gravity might be the key to controlling time itself, and why the future of humanity might depend on learning to navigate not just through space, but through time. You all see how massive objects don't just bend space. They bend the very flow of existence, creating temporal landscapes where the rate of aging, the speed of thought, and even the nature of causality depend on your distance from gravitational sources. And you all discover why understanding gravitational time dilation might be essential for humanity's survival as we venture beyond Earth into cosmic environments where time flows at radically different rates. If you're fascinated by the idea that time itself is under the control of massive objects, that your personal timeline is constantly being modified by gravity, and that the universe might be filled with natural time travel opportunities, subscribe and hit thumbs up. And here is a question that will take on new meaning as we explore temporal manipulation. If you could slow down your personal timeline by positioning yourself near a massive object, watching centuries pass in what feels like days, would you choose to be a time traveler, or would you prefer to age normally alongside the rest of humanity? Comment below. I'll pin the most thoughtful answer, because in a universe where time is flexible, these choices might soon become real options. But we're getting ahead of ourselves. To understand how massive objects steal time, we first need to understand what time actually is. Not the time we measure with clocks and calendars, but the fundamental temporal dimension that weaves together with space to create the fabric of reality itself. Now let's begin this journey into the heart of time, where we all discover that everything you thought you knew about the flow of existence is about to change forever. Chapter 1. The Fabric of Space-Time. To understand how massive objects can slow down time, we must first shatter our intuitive understanding of time as something separate from space, flowing uniformly throughout the universe like an invisible river, carrying all events along at the same rate. The revolutionary insight of Einstein's relativity is that time and space are not separate entities, but are woven together into a single dynamic fabric called space-time, a four-dimensional continuum where time serves as the fourth dimension, as real and manipulable as length, width, and height. This unification of space and time represents one of the most profound conceptual revolutions in human thought. For thousands of years, humans understood space as the stage where events occur and time as the universal clock measuring when those events happen. Newton's mechanics treated space as absolute and unchanging, time as universal and constant, flowing at the same rate everywhere, regardless of motion or gravitational fields. This intuitive picture seemed so obviously correct that questioning it appeared absurd. But Einstein's special theory of relativity, published in 1905, revealed that this intuitive understanding was fundamentally flawed. Time and space are not independent. They are intimately connected, with the flow of time depending on motion through space and the geometry of space depending on the flow of time. What we experience as separate dimensions are actually different aspects of a unified four-dimensional reality, where every event has coordinates in both space and time. The mathematical framework of space-time treats events not as happening at a place and at a time, but as occurring at specific points in four-dimensional space-time. Your existence right now reading these words corresponds to a specific space-time coordinate, 3 spatial dimensions specifying your location, plus 1 temporal dimension specifying when this reading is happening. But here's the crucial insight. These coordinates are not absolute. They depend on the reference frame of the observer. Special relativity demonstrated that observers moving at different velocities relative to each other will disagree about the spatial and temporal coordinates of the same events. What one observer measures as simultaneous, another observer in motion will measure as happening at different times. What one observer measures as a specific spatial distance, another will measure as a different distance, with time intervals also changing to compensate. Space and time are relative, but space-time, the combination of space and time, remains absolute. This relativistic mixing of space and time creates phenomena that seem impossible from our everyday perspective. Time dilation means that moving clocks run slow, not because the clocks are broken, but because time itself flows differently in different reference frames. Length contraction means that objects appear shorter when moving at high velocities, not because they physically compressed, but because space itself behaves differently for observers in relative motion. But special relativity only addresses the effects of uniform motion through space-time. The even more profound insights come from general relativity, Einstein's theory of gravitation, published in 1915, which revealed that massive objects don't just exist in spacetime. They actively curve and distort the fabric of spacetime itself. This curvature is what we experience as gravitational force, but it's actually the geometry of spacetime responding to the presence of mass and energy. The central insight of general relativity is summarized in physicist John Wheeler's famous phrase, "Matter tells spacetime how to curve, and curved spacetime tells matter how to move." Massive objects create depressions, warps, and distortions in the fabric of spacetime, like heavy balls placed on a stretched rubber sheet. These distortions guide the motion of other objects, creating what we observe as gravitational attraction, but they also affect the flow of time itself. This is where gravitational time dilation emerges as a fundamental consequence of spacetime geometry. In curved spacetime near massive objects, the temporal dimension becomes stretched relative to the spatial dimensions. Clocks embedded in stronger gravitational fields, deeper in the spacetime curvature created by massive objects, literally run slower than identical clocks in weaker gravitational fields. This isn't an illusion or a measurement error. It's a fundamental feature of how time operates in curved spacetime. The mathematics that describe this temporal stretching come from the metric tensor, a mathematical object that specifies the geometry of spacetime at every point. Near a massive object like Earth, the metric tensor has components that directly relate the rate of time flow to the strength of the gravitational field. The famous Schwarzschild solution to Einstein's field equations provides precise formulas for calculating exactly how much time slows down at any distance from a spherically symmetric massive object. For a static observer at distance r from a mass m, time flows at a rate determined by the factor skirt, 1 twag meir K2, compared to time at infinite distance from the mass. Here g is Newton's gravitational constant, c is the speed of light, and the expression reveals how gravitational time dilation depends directly on the mass of the gravitating object and inversely on the distance from that mass. Larger masses create stronger time dilation, and closer proximity to any mass creates stronger time dilation. This mathematical relationship means that Earth's gravitational field is constantly creating a temporal gradient. Time flows slightly slower at sea level than at mountain tops, slightly slower in valleys than on hills, slightly slower in your basement than in your attic. The differences are tiny, approximately 1.1 parts in 1016 per meter of height difference. But they're real, measurable, and cumulative over large scales and long time periods. The fabric of space-time around Earth resembles a shallow depression, with time flowing slowest at Earth's surface and gradually speeding up with altitude and distance. The International Space Station, orbiting approximately 400 kilometers above Earth's surface, experiences time flowing about 45 microseconds per day faster than at Earth's surface. GPS satellites at 20,000 kilometers altitude experience time flowing about 38 microseconds per day, faster than ground-based observers. But these everyday examples pale in comparison to the extreme space-time curvatures created by more massive and dense objects. Near neutron stars, which pack more mass than our Sun into spheres only 20 kilometers in diameter, space-time curvature becomes so extreme that time dilation effects become dramatic. A clock on the surface of a typical neutron star would run approximately 30% slower than a clock far from the neutron star as gravitational influence. The most extreme space-time curvatures occur near black holes, where the fabric of space-time is warped so severely that time dilation approaches infinite values. At the event horizon of a black hole, time dilation becomes so extreme that time appears to stop completely from the perspective of distant observers. An astronaut falling toward a black hole would experience time flowing normally from their perspective, but observers far from the black hole would see the astronaut's clock slowing down, their movements becoming sluggish, their aging process grinding to a halt as they approach the event horizon. This extreme time dilation near black holes creates one of the most mind-bending consequences of general relativity: gravitational time travel. Someone who ventures close to a black hole and returns will have aged less than people who remain far from the black hole's influence. This isn't science fiction. It's a direct consequence of the mathematics of curved spacetime, confirmed by every test of general relativity ever performed. The fabric of spacetime also exhibits dynamic properties that create additional temporal effects. Gravitational waves, ripples in spacetime itself created by accelerating masses, carry energy and momentum while temporarily distorting the flow of time as they pass. When gravitational waves from merging black holes or neutron stars sweep through Earth, they create tiny, brief modifications in local time flow that can be detected by instruments sensitive enough to measure space-time distortions smaller than 1/10th the width of a proton. The quantum mechanical properties of spacetime add yet another layer of complexity to temporal behavior near massive objects. Quantum field theory in curved spacetime predicts that virtual particle pairs near event horizons can become separated permanently, creating Hawking radiation that carries away energy and information while modifying local spacetime geometry. These quantum effects create additional time dilation mechanisms that operate at the smallest scales while influencing macroscopic temporal flow. Understanding spacetime as a dynamic, deformable fabric revolutionizes our comprehension of existence itself. We don't live in space and move through time. We live in spacetime, and our movement through this four-dimensional continuum determines every aspect of our temporal experience. Massive objects around us are constantly sculpting the temporal landscape, creating hills and valleys in the flow of time that shape our aging, our biological rhythms, and potentially our consciousness itself. But recognizing spacetime as the foundation of temporal experience raises immediate questions about how we can measure and verify these effects. How do scientists detect time dilation that operates at such subtle levels? What experiments have proven that massive objects really do slow down time? How do we know that our clocks aren't just malfunctioning when they show these relativistic effects? Chapter 2. Measuring stolen time. The detection and measurement of gravitational time dilation represents one of the most precise experimental achievements in the history of science, requiring instruments capable of detecting temporal changes smaller than a single second across the entire age of the universe. The development of atomic clocks, devices that measure time by counting the oscillations of atoms trapped in electromagnetic fields, has pushed the boundaries of measurement precision to levels that seem almost supernatural, revealing gravitational time dilation operating at scales from laboratory benchtops to cosmic distances. Atomic clocks operate by exploiting the fundamental quantum mechanical property that electrons and atoms can only exist at specific discrete energy levels. When electrons transition between these energy levels, they absorb or emit electromagnetic radiation at precisely defined frequencies that serve as natural metronomes, oscillating billions of times per second with extraordinary regularity. The most advanced atomic clocks use cesium-133 atoms, optical lattice clocks with strontium atoms, or trapped ion systems that achieve frequency stability approaching 1 part in 1018. 2. Put this precision in perspective. If such a clock had been running since the Big Bang 13.8 billion years ago, it would be accurate to within less than 1 second today. This extraordinary precision makes atomic clocks sensitive to gravitational time dilation effects that change the flow of time by amounts so small they seem impossible to detect. Yet these effects are not just detectable, but have become routine measurements in modern physics laboratories. The first successful detection of gravitational time dilation was achieved by Robert Pound and Glenn Rebka at Harvard University in 1960, using the ultra-precise technique of Mexbauer spectroscopy to measure the gravitational redshift of gamma rays traveling just 22.5 meters up a tower. When gamma rays climb against Earth's gravitational field, they lose energy and their frequency decreases, exactly as predicted by general relativity for photons escaping from gravitational wells. This frequency shift corresponds to the time dilation experienced by clocks at different heights in Earth's gravitational field. The Pound-Rebka experiment confirmed Einstein's prediction to within 1% accuracy, but subsequent experiments have pushed the precision to extraordinary levels. In 1976, Smithsonian Astrophysical Observatory scientists Robert Vesed and Martin Levine launched a hydrogen maser atomic clock on a rocket to an altitude of 10,000 kilometers directly, measuring gravitational time dilation with 0.01% precision by comparing the rocket clock's frequency with identical clocks on Earth's surface. Modern optical atomic clocks have revolutionized gravitational time dilation measurements by achieving unprecedented frequency stability and accuracy. These devices trap individual atoms in optical lattice created by intersecting laser beams, isolating them from environmental disturbances while interrogating their quantum transitions with laser light. The resulting frequency measurements are so precise that they can detect gravitational time dilation across height differences of just a few centimeters. In 2010, researchers at the National Institute of Standards and Technology, NIST, used optical atomic clocks to measure gravitational time dilation across a height difference of just 33 centimeters, about the height of a typical desk. The experiment confirmed that time flows measurably slower at the lower position, with the time difference accumulating at a rate of approximately 4 parts in 1017 per centimeter of height difference. This extraordinary sensitivity demonstrates that gravitational time dilation operates at the scale of ordinary human environments. Even more remarkably, in 2022, scientists achieved gravitational time dilation measurements across height differences of just 1 millimeter, smaller than a grain of rice. Using ultra-stable optical atomic clocks and sophisticated laser interferometry techniques, researchers detected the tiny change in time flow created by moving clocks less than the thickness of a credit card closer to Earth's center. This achievement represents the ultimate demonstration that gravitational time dilation is not an exotic effect limited to extreme astronomical environments, but a fundamental feature of spacetime operating at everyday scales. The practical applications of gravitational time dilation measurements extend far beyond academic physics. The Global Positioning System, GPS, provides the most visible example of how accounting for gravitational time dilation has become essential for modern technology. GPS satellites orbit at approximately 20,000 kilometers altitude, where Earth's gravitational field is weaker than at the surface. This causes satellite clocks to run approximately 45 microseconds per day faster than identical clocks on Earth's surface. Without correcting for this gravitational time dilation, GPS position calculations would accumulate errors of approximately 11 kilometers per day, making the system completely useless for navigation. GPS satellites therefore continuously adjust their timing signals to account for both gravitational time dilation and the special relativistic time dilation caused by their orbital motion. The result is a global navigation system that relies fundamentally on general relativity for its operation. The measurement of gravitational time dilation has also enabled tests of general relativity as predictions in increasingly extreme environments. Observations of binary pulsar systems, pairs of neutron stars orbiting each other while emitting precisely timed radio pulses, have confirmed gravitational time dilation effects in strong gravitational fields. The pulsar PSR 1913+16, discovered by Russell Hulse and Joseph Taylor, shows orbital decay precisely matching general relativity's predictions for energy loss through gravitational wave emission, while also exhibiting the time dilation effects expected in the neutron star's intense gravitational fields. Recent gravitational wave detections by the LIGO and Virgo collaborations have opened new avenues for studying extreme gravitational time dilation. The gravitational wave signals from merging black holes and neutron stars carry information about spacetime curvature in regions where gravitational time dilation approaches extreme values. Analysis of these signals provides direct measurements of how time flows in the strongest gravitational fields accessible to human observation. The development of transportable optical atomic clocks has enabled geodetic applications of gravitational time dilation measurements. Because the flow of time depends on gravitational potential, precise time measurements can map Earth's gravitational field with extraordinary accuracy. This technique, called relativistic geodesy, uses atomic clocks to measure tiny variations in Earth's gravitational field caused by underground mass distributions, ocean currents, and tectonic activity. Experimental searches for violations of general relativity have used gravitational time dilation measurements to test alternative theories of gravitation. Some modified theories of gravity predict deviations from Einstein's predictions for gravitational time dilation, making precise time measurements a powerful tool for testing fundamental physics. To date, all such tests have confirmed general relativity's predictions with increasing precision, strengthening our confidence in Einstein's description of spacetime geometry. The measurement of gravitational time dilation has also enabled investigations of the relationship between gravity and quantum mechanics. Experiments using atomic interferometry, techniques that exploit the wave nature of matter to create ultra-sensitive gravimeters, can measure gravitational time dilation while simultaneously probing quantum mechanical effects in gravitational fields. These experiments explore the frontier where general relativity and quantum mechanics intersect, potentially revealing new physics beyond current theoretical understanding. Future gravitational time dilation experiments will push measurement precision to even more extraordinary levels. Proposed space-based atomic clock experiments could achieve frequency stability approaching 1 part in 1019, enabling tests of general relativity in completely unexplored parameter regimes. Such precision would allow detection of gravitational time dilation effects from individual asteroids, investigation of temporal variations in Earth's gravitational field, and searches for exotic physics beyond the standard model of particle physics. The technological applications of ultra-precise time measurement continue to expand beyond fundamental physics research. Gravitational time dilation measurements enable improved geological surveys, underground resource exploration, and monitoring of groundwater levels through their effects on local gravitational fields. The same atomic clock technology used to measure gravitational time dilation also enables quantum sensing applications in navigation, communication, and computation. But perhaps the most profound implication of measuring gravitational time dilation with such extraordinary precision is philosophical rather than technological. These experiments demonstrate that time itself, our most basic experience of temporal flow, is not fundamental or universal, but depends on our position in space-time. Every measurement of gravitational time dilation confirms that our intuitive understanding of time as absolute and uniform is an approximation that breaks down when examined with sufficient precision. The ability to measure stolen time with atomic clock precision raises immediate questions about the practical implications of gravitational time dilation for human life and consciousness. How do these temporal effects influence biological processes, aging, and potentially awareness itself? Can we harness gravitational time dilation for practical applications? And what would it mean to live in a world where time flows at different rates depending on your gravitational environment? Chapter 3. Rhythms in gravitational fields. Every cell in your body operates according to molecular clocks that count time through biochemical oscillations. But these biological rhythms exist within the curved spacetime created by Earth's gravitational field, raising profound questions about how gravitational time dilation affects the fundamental processes of life. Your heartbeat, neural firing patterns, circadian cycles, and cellular metabolism all depend on precisely timed molecular interactions. That must somehow account for the fact that time itself flows at different rates, depending on your position relative to massive objects. The discovery that life relies on sophisticated timekeeping mechanisms at every scale, from DNA replication to ecosystem cycles, has revealed biology as fundamentally temporal science. Circadian rhythms regulate sleep-wake cycles, hormone production, body temperature, and countless physiological processes through molecular clockwork involving transcriptional feedback loops that oscillate with periods close to 24 hours. These biological clocks are so precise that they can detect seasonal changes in daylight duration and adjust physiological processes accordingly. But circadian rhythms evolved within Earth's gravitational environment, where time flows at a rate determined by our planet's mass and our distance from its center. This raises the extraordinary question: how would biological clocks function in different gravitational environments where time flows at different rates? Would your circadian rhythm speed up or slow down if you lived near a neutron star? How would your metabolism respond to the extreme time dilation near a black hole? The relationship between biological time and physical time becomes particularly intriguing when considering the quantum mechanical foundations of biochemistry. Enzymatic reactions, protein folding, and DNA transcription all depend on quantum mechanical processes, including electron tunneling, proton transfer, and molecular vibrations that operate according to fundamental quantum mechanical timescales. These quantum processes provide the molecular clockwork that drives biological rhythms, but they also respond to the local flow of time determined by gravitational fields. Recent discoveries in quantum biology have revealed that living systems routinely exploit quantum mechanical phenomena for biological function. Photosynthesis uses quantum coherence to achieve near-perfect energy transfer efficiency. Bird navigation appears to rely on quantum entanglement in cryptochrome proteins. Even microtubules in neurons might utilize quantum processes for information processing. These quantum biological mechanisms operate according to timescales determined by fundamental physical constants. But those timescales are modified by gravitational time dilation in ways that could subtly influence biological function. Consider the implications for aging processes, which depend on the accumulation of molecular damage over time. DNA repair mechanisms operate according to biological clocks that determine how quickly cells can correct replication errors, fix radiation damage, and maintain chromosomal integrity. In stronger gravitational fields, where time flows slower, these repair processes would operate more slowly from the perspective of distant observers, potentially altering the rate of biological aging in ways that depend on gravitational environment. The cardiovascular system provides another example of biological timing sensitive to gravitational effects. Heart rate variability, the subtle changes in timing between heartbeats, reflects complex feedback loops between the autonomic nervous system and cardiac pacemaker cells. These timing variations carry information about health status and stress levels, but they also precisely timed biological processes that would be affected by gravitational time dilation in environments with significantly different gravitational fields. Neurological processes present perhaps the most intriguing connections between gravitational time dilation and biological function. Neural action potentials propagate through axons at speeds determined by biochemical and electrical processes that depend on molecular timescales. Synaptic transmission involves precise timing of neurotransmitter release and uptake that occurs over microsecond timescales. Even consciousness itself might depend on temporal coordination between different brain regions that requires precise neural timing. The question of how consciousness would be affected by gravitational time dilation touches on fundamental mysteries about the relationship between physical processes and subjective experience. If neural processes slow down in stronger gravitational fields, would conscious experience also slow down? Would thoughts feel sluggish to someone near a massive object? Or would consciousness automatically adjust to maintain normal subjective experience regardless of external time flow? Some theories of consciousness propose that awareness emerges from quantum mechanical processes in neural microtubules that operate according to fundamental quantum timescales. If these quantum consciousness theories are correct, then gravitational time dilation could directly affect the rate of conscious information processing, potentially altering not just the speed of thought but the nature of conscious experience itself in different gravitational environments. The practical implications for space travel and planetary colonization are staggering. Astronauts spending extended periods in different gravitational environments might experience subtle but cumulative changes in biological rhythms, aging rates, and potentially cognitive function. A colony on Mars, where gravitational time dilation is slightly different from Earth due to Mars's smaller mass, might develop biological adaptations over generations that optimize human physiology for the Martian gravitational environment. Near more extreme gravitational environments, these effects could become dramatic. Hypothetical space stations positioned near neutron stars or in controlled orbits around black holes could experience such severe gravitational time dilation that biological processes would be dramatically slowed from external perspectives. This could create opportunities for extended lifespans, accelerated healing through time dilation effects, or even forms of suspended animation achieved through gravitational rather than biological means. The study of biological rhythms in variable gravitational fields has already begun through experiments on the International Space Station, where microgravity eliminates many gravitational effects while maintaining Earth's overall gravitational time dilation. Astronauts exhibit disrupted circadian rhythms, altered cardiovascular function, and modified neural processing that might partly result from the changed gravitational environment's effects on biological timing mechanisms. Recent research on extremophile organisms, life forms that thrive in extreme environments, provides insights into how biology might adapt to unusual gravitational conditions. Organisms living deep underground experience slightly slower time flow than surface life due to stronger gravitational fields, while high-altitude organisms experience slightly faster time flow. Though these effects are tiny, they might drive subtle evolutionary adaptations in molecular clockwork that optimizes biological function for specific gravitational environments. The potential for gravitational cryotherapy, using controlled gravitational time dilation for medical applications, represents an entirely new frontier in medicine. If biological processes can be slowed through gravitational time dilation, this might provide treatment options for conditions involving excessive cellular activity, rapid aging, or accelerated disease progression. Conversely, regions of reduced gravity might accelerate healing processes or enhance cognitive function through faster neural processing. Laboratory experiments using centrifuges to create enhanced gravitational fields have already demonstrated measurable effects on biological systems. Cell cultures exposed to increased gravitational acceleration show modified gene expression patterns, altered protein synthesis rates, and changed metabolic activity that suggest direct gravitational influences on biological timing mechanisms. These experiments provide the first evidence that life processes are indeed sensitive to gravitational environment in ways that extend beyond simple mechanical effects. The development of artificial gravity systems for long-duration space missions must account for the Fortschrittensfaktor relationship between gravitational field strength and biological rhythms. Rotating spacecraft that create artificial gravity through centrifugal acceleration might need to optimize rotation rates, not just for comfortable mechanical conditions, but also for maintaining healthy biological timing, mechanisms that evolved in Earth as specific gravitational environment. Future research into gravitational biology will require developing techniques to measure biological processes with precision comparable to atomic clocks, detecting subtle changes in cellular timing mechanisms that could reveal how life adapts to different gravitational time flows. Advanced microscopy techniques, single-molecule measurement methods, and quantum sensing technologies might enable direct observation of how gravitational time dilation affects molecular biological processes. The implications extend beyond human biology to encompass all life forms that might exist throughout the universe. If life is common throughout the cosmos, it must have evolved to function in diverse gravitational environments where time flows at dramatically different rates. Understanding how biology adapts to gravitational time dilation might provide insights into the forms life might take near massive objects like neutron stars or in the extreme gravitational environments of galactic centers. But studying biological rhythms in gravitational fields raises fundamental questions about the nature of life itself in a universe where time is flexible. How do we define biological processes when the rate of those processes depends on gravitational environment? What does it mean for organisms to age when aging occurs at different rates depending on position in spacetime? How do we understand evolution and natural selection in environments where time itself evolves? Chapter 4. Time dilation. Our solar system is a vast laboratory for gravitational time dilation, where every planet, moon, and asteroid creates its own unique temporal environment. The Sun's massive gravitational field dominates the system's overall time flow, while each celestial body contributes additional temporal complexity through its own gravitational influence. Understanding this cosmic clockwork reveals that space travel isn't just about covering distance. It is about navigating through time itself, where your aging rate and biological rhythms depend on your orbital trajectory and gravitational environment. The Sun, containing 99.86% of the solar system's total mass, creates the primary gravitational time dilation affecting all objects within its influence. At Earth's orbital distance, approximately 150 million kilometers from the Sun, solar gravitational time dilation causes clocks to run about 2 parts in 10^8 slower than they would in the absence of the Sun's gravity. While this seems like a tiny effect, it accumulates to approximately 66 seconds per year, meaning that every year, Earth's position in the solar system causes us to age about 1 minute less than we would in flat spacetime. This solar time dilation varies significantly with orbital distance, creating different temporal zones throughout the solar system. Mercury, orbiting closest to the Sun at an average distance of 58 million kilometers, experiences the strongest solar time dilation. Clocks on Mercury's surface run approximately 3 parts in 108 slower than clocks far from the Sun's influence. In contrast, Pluto at its farthest point experiences solar time dilation of only about 0.2 parts in 108, making time flow noticeably faster in the outer solar system compared to interplanetary regions. Each planet contributes its own gravitational time dilation that combines with solar effects to create complex temporal landscapes. Earth's gravitational field causes surface clocks to run approximately 7 parts in 10^10 slower than clocks at infinite distance. This seems negligible compared to solar effects, but Earth's gravity creates dramatic time variations over relatively short distances. The difference between sea level and the summit of Mount Everest corresponds to about 30 microseconds per year in aging rate. Jupiter, with its massive gravitational field, creates some of the most extreme planetary time dilation in the solar system. Surface gravity on Jupiter is about 2.5 times stronger than Earth's, causing clocks to run approximately 2 parts in 109, slower than on Earth. A hypothetical observer on Jupiter's surface would age measurably slower than someone on Earth, with the difference accumulating to several seconds per year. Jupiter's moons experience even more complex time dilation effects as they orbit within the planet's gravitational well, while simultaneously orbiting the Sun. The Galilean moons of Jupiter provide fascinating examples of hierarchical gravitational time dilation. Io, orbiting closest to Jupiter, experiences the strongest Jovian time dilation while also being deep within the Sun's gravitational well. Europa, Ganymede, and Callisto each exist in slightly different temporal environments, determined by their orbital distances from Jupiter. These time differences, while small, would accumulate over geological timescales to create measurable effects on any processes occurring on these moons. Saturn's system presents similar temporal complexity, with the massive planet creating significant gravitational time dilation while its numerous moons and rings exist in graduated temporal zones. Titan, Saturn's largest moon, has its own appreciable gravitational field that adds to the complex time dilation environment. The intricate dance of Saturn's moons through these overlapping gravitational time fields creates one of the most complex temporal environments in the solar system. The asteroid belt represents a region of relatively weak but variable gravitational time dilation, where thousands of small bodies each contribute tiny temporal effects. Large asteroids like Ceres and Vesta create localized regions of slightly slower time, while the overall sparse density of the asteroid belt means that spacecraft traversing this region experience relatively uniform temporal conditions, dominated by solar gravity. Mars presents particularly interesting time dilation characteristics for potential human colonization. With about 11% of Earth's mass and 38% of Earth's surface gravity, Mars creates weaker gravitational time dilation than Earth. Colonists on Mars would age slightly faster than people on Earth, approximately 2.4 microseconds per day faster. Over a human lifetime, this difference would accumulate to about 0.6 seconds. A negligible personal effect, but a measurable physical phenomenon that demonstrates how gravitational environment directly affects biological aging rates. The outer gas giants Uranus and Neptune create their own distinctive temporal environments in the far solar system. Their large masses generate significant gravitational time dilation despite their distance from the Sun, while their numerous moons exist in complex gravitational hierarchies that create graduated time zones throughout each planetary system. The extreme distance from the Sun means these regions experience weaker solar time dilation, making planetary gravitational effects more dominant in determining local time flow. Spacecraft trajectories through the solar system must account for time dilation effects that accumulate during long-duration missions. The Voyager spacecraft, launched in 1977 and now traveling through interstellar space, have experienced slightly different aging rates than Earth due to their changing gravitational environments. While the effects are tiny, they represent measurable time dilation accumulated over decades of travel through varying gravitational fields. Future missions to study the Sun will encounter some of the most extreme solar time dilation accessible to human technology. The Parker Solar Probe, launched in 2018, will approach within 7 million kilometers of the Sun's surface, experiencing gravitational time dilation approximately 20 times stronger than at Earth's orbital distance. During its closest approaches, the spacecraft's clocks will run measurably slower than Earth clocks, creating tiny but detectable temporal effects. Proposed missions to Jupiter's moons and Saturn system will need to account for complex hierarchical time dilation effects when coordinating operations and communications. Spacecraft operating in these environments will experience time flow that varies with their orbital position, creating challenges for mission timing and navigation that require careful consideration of relativistic effects. The prospect of asteroid mining introduces practical considerations about time dilation in commercial space operations. Mining operations on large asteroids would experience slightly different time flow than Earth-based control centers, creating potential synchronization challenges for remote operations. While the effects would be tiny for most asteroids, they demonstrate how gravitational time dilation will become a practical consideration as human economic activity expands throughout the solar system. Solar system time dilation effects also influence astronomical observations and measurements. When Earth-based telescopes observe phenomena on other planets or moons, they must account for the different time flow rates at those locations. This becomes particularly important for precise timing measurements of planetary phenomena, where gravitational time dilation can introduce systematic errors if not properly accounted for. The development of precision navigation systems for interplanetary travel requires incorporating gravitational time dilation into trajectory calculations. Future spacecraft equipped with atomic clocks will need to continuously adjust their timing systems as they move through varying gravitational fields, ensuring accurate position determination and communication with Earth despite the constantly changing temporal environment. The study of time dilation throughout the solar system provides a testbed for understanding how temporal effects operate in complex gravitational environments. These measurements help verify general relativity as predictions, while preparing for future exploration of more extreme gravitational environments around other stars, neutron stars, and black holes where time dilation effects become dramatically more significant. But exploring time dilation within our solar system raises broader questions about temporal navigation in cosmic environments. How do we coordinate activities across multiple temporal zones? What happens when human civilization expands to regions with dramatically different time flow rates? How do we maintain synchronization across a species distributed throughout environments where time itself behaves differently? Chapter 5. Extreme temporal environments. Beyond the gentle time dilation of our solar system lie cosmic environments so extreme the time itself becomes almost unrecognizable. Regions near neutron stars, black holes, and other exotic objects, where gravitational fields are so intense that seconds can stretch into years, where the familiar flow of time breaks down completely, and where the very concept of simultaneous events loses all meaning. These extreme temporal environments reveal time dilation not as a subtle correction to everyday physics, but as a fundamental feature of reality that can dominate every aspect of existence. Neutron stars represent some of the most accessible extreme temporal environments in the universe. These incredibly dense objects, formed when massive stars collapse and compress matter to nuclear densities, pack more mass than our Sun into spheres only 20 kilometers in diameter. The resulting gravitational fields are so intense that they create time dilation effects that would be immediately noticeable to any observer capable of surviving in such environments. On the surface of a typical neutron star with 1.4 solar masses, gravitational time dilation causes clocks to run approximately 30% slower than clocks far from the neutron star's influence. This means that if you could somehow stand on a neutron star's surface and look up at distant space through a telescope, you would see the rest of the universe appearing to run in fast forward. Stars would evolve more rapidly, planetary orbits would appear accelerated, and any electromagnetic signals from distant civilizations would appear blue-shifted to higher frequencies. But the extreme conditions on neutron stars create time dilation effects that vary dramatically across very short distances. The difference in gravitational time dilation between the neutron star's surface and a point just 1 kilometer above the surface would be measurable with atomic clocks. This creates temporal gradients so steep that objects falling toward neutron stars would experience differential time dilation across their extent, a phenomenon known as temporal tidal effects, where different parts of the same object age at noticeably different rates. The magnetospheres around neutron stars add another layer of complexity to their temporal environments. These objects often possess magnetic fields trillions of times stronger than Earth's, creating additional relativistic effects that can modify time dilation through electromagnetic field energy contributions to space-time curvature. Pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation, create temporal environments that combine extreme gravitational time dilation with rapidly changing electromagnetic fields that pulse with millisecond precision. Black holes represent the ultimate extreme in temporal environments, where gravitational time dilation approaches infinite values as observers approach the event horizon. The mathematics of black hole spacetime, described by the Schwarzschild metric, predict that time dilation increases without limit as the distance to the black hole center decreases. At the event horizon itself, time dilation becomes infinite from the perspective of distant observers. Time appears to stop completely. This infinite time dilation at black hole event horizons creates one of the most mind-bending consequences of general relativity. The experience of watching someone fall into a black hole would never reach completion from an outside observer's perspective. As the falling person approaches the event horizon, they would appear to slow down, redshift, and fade from view. But they would never actually be seen to cross the event horizon because time dilation there becomes infinite. From the perspective of someone falling into a black hole, however, the experience remains finite and normal until reaching the singularity at the center. The falling observer's clocks continue running normally from their own reference frame, and they cross the event horizon in finite time as measured by their own clocks. This creates the famous black hole paradox, where the same event crossing the event horizon appears to take infinite time from one perspective and finite time from another. The region just outside black hole event horizons, known as the photon sphere for Schwarzschild black holes, represents a zone where even light must orbit the black hole rather than escape to infinity. Time dilation in this region approaches the extreme values found at the event horizon, creating temporal environments where hours for a local observer could correspond to years or even decades for distant observers. This extreme time differential makes the photon sphere a natural location for hypothetical time travel scenarios. Rotating black holes, described by the chronometric, create even more complex temporal environments through the additional effects of frame dragging. The rotation of these black holes literally drags space-time around with them, creating regions where the flow of time depends not just on gravitational strength, but also on the direction of motion relative to the black hole's rotation. These effects create temporal complexity that goes beyond simple time dilation to include modifications in how time and space mix in the immediate vicinity of rotating massive objects. The ergosphere of a rotating black hole, the region outside the event horizon where space-time is dragged along with the black hole's rotation, represents a unique temporal environment where certain forms of energy extraction become possible. The Penrose process allows objects to extract rotational energy from black holes by dropping matter into the ergosphere in carefully designed trajectories, potentially powering advanced civilizations while simultaneously creating complex time dilation effects. Gamma ray bursts, among the most energetic phenomena in the universe, create temporary extreme temporal environments during their brief but intense emissions. The enormous energy densities achieved during these events approach the levels where space-time curvature becomes significant, potentially creating brief periods of measurable gravitational time dilation, even at astronomical distances from the source. White holes, hypothetical objects that represent the time reverse of black holes, would create temporal environments where time dilation effects operate in reverse. While white holes remain theoretical and have never been observed, their mathematical description suggests regions where time would appear to run faster rather than slower, creating temporal acceleration rather than deceleration effects for nearby observers. Wormholes, if they exist, would create the most exotic temporal environments imaginable. Regions where space-time connects distant locations through traversable passages that could potentially link different epochs as well as different locations. The temporal effects within wormhole throats would depend on the specific geometry and exotic matter content that stabilizes these hypothetical structures. The study of extreme temporal environments has practical implications for understanding the fundamental limits of physics and technology. These environments represent natural laboratories where general relativity operates in regimes impossible to recreate artificially, providing tests of our understanding of space-time physics under the most extreme conditions accessible to observation. Advanced civilizations capable of surviving near neutron stars or black holes would need to develop technologies specifically adapted to extreme time dilation environments. Communication systems would need to account for vast temporal differences between different locations. Energy production systems would need to operate efficiently in highly curved spacetime, and biological systems would need adaptation mechanisms for surviving in environments where time flows at dramatically different rates. The detection and study of extreme temporal environments relies on astronomical observations that can indirectly measure time dilation effects through their influence on electromagnetic radiation, gravitational waves, and particle emissions. X-ray observations of matter falling into black holes reveal time dilation effects through the observed dynamics of accretion disks, while gravitational wave detections provide direct measurements of space-time curvature in regions where extreme time dilation operates. But contemplating extreme temporal environments raises fundamental questions about the nature of existence in regions where time itself behaves in ways completely alien to human experience. How would consciousness operate in environments with such extreme time dilation? What would it mean to think, to remember, to experience duration in regions where time flows at dramatically different rates? How do we even define existence in temporal environments that challenge our most basic concepts of sequence, causality, and the flow of time itself? Chapter 6. Gravitational Time Machines. The precise control of gravitational time dilation opens possibilities for creating genuine time machines, not the science fiction devices that transport you backward to change the past, but scientific instruments that allow controlled travel into the future by manipulating the flow of time itself through gravitational effects. These gravitational time machines operate according to well-established physics, requiring no exotic matter or speculative technology, only the ability to position yourself in strong gravitational fields and return to weaker fields after sufficient time has passed. The fundamental principle behind gravitational time machines emerges directly from the mathematics of general relativity. If you can position yourself in a region where time flows slower due to strong gravitational fields, then return to a region where time flows faster, you will have traveled into the future relative to the environment you left behind. The amount of time travel achieved depends on the strength of the gravitational field and the duration spent within it, with the effects being cumulative and irreversible. The simplest gravitational time machine would use a massive object like a planet or star to create the necessary time dilation. By orbiting close to a massive body where gravitational time dilation is significant, then returning to a distance where gravitational effects are weaker, a traveler could experience differential aging that effectively constitutes forward time travel. The closer the orbit to the massive object and the longer the duration of the journey, the more dramatic the time travel effect. Consider a hypothetical journey to a neutron star located relatively close to our solar system. Traveling to a stable orbit just above the neutron star's surface, where time runs approximately 30% slower than on Earth, and remaining there for what feels like 1 year to the traveler would result in returning to find that about 1.4 years had passed on Earth. While this might seem like a modest effect, the cumulative impact over longer stays becomes dramatic. A decade near the neutron star would correspond to about 14 years passing on Earth. Black holes offer even more extreme gravitational time machine capabilities, though the engineering challenges become formidable. A carefully planned orbit near a black hole's event horizon, where gravitational time dilation can approach extreme values, could create time travel effects measured in centuries or millennia for journey durations of months or years as experienced by the traveler. The limit case of approaching infinite time dilation at the event horizon offers theoretically unlimited forward time travel. The practical implementation of gravitational time machines faces enormous technological challenges. Reaching neutron stars or black holes requires propulsion systems capable of accelerating spacecraft to significant fractions of light speed while carrying sufficient fuel and life support for extended journeys. The extreme gravitational environments around these objects create tidal forces that would tear apart conventional spacecraft, requiring exotic materials and designs to survive close approaches. Nevertheless, some gravitational time machine concepts might be achievable with advanced but conceivable technology. Artificial gravity wells created by concentrating large amounts of matter in small volumes could generate significant time dilation without requiring travel to exotic astronomical objects. Theoretical calculations suggest that concentrating the mass of an asteroid into a sphere a few kilometers in diameter could create measurable time dilation effects, accessible to spacecraft with advanced propulsion systems. The twin paradox of special relativity provides a well-known example of time travel achieved through relative motion, but gravitational time machines offer advantages over purely kinematic approaches. While achieving significant time dilation through high-speed travel requires enormous energies to approach relativistic velocities, gravitational time dilation can achieve similar effects through position in spacetime rather than motion through spacetime. This potentially makes gravitational time travel more energy efficient than kinematic time travel for achieving large temporal displacements. Hybrid gravitational kinematic time machines might offer the most practical approach to significant time travel effects. By combining high-speed travel with positioning in strong gravitational fields, travelers could achieve time dilation effects greater than either method alone. A spacecraft accelerating to high velocity while diving close to a massive object could experience combined time dilation, effects that multiply the temporal displacement achieved through each mechanism separately. The discovery of techniques for manipulating space-time geometry could revolutionize gravitational time machine design. Theoretical proposals for creating artificial gravitational fields through exotic matter configurations, electromagnetic field manipulation, or quantum effects could enable construction of compact time machines that don't require travel to astronomical distances. While such technologies remain highly speculative, they represent potential pathways to practical gravitational time travel. Quantum gravitational effects might offer additional mechanisms for temporal manipulation at small scales. Some theories predict that quantum fluctuations in space-time geometry could create microscopic regions of altered time flow that might be amplified through technological means. While these effects would initially be tiny, advanced quantum engineering might enable their enhancement to macroscopic levels suitable for practical time travel applications. The development of gravitational time machines raises profound questions about causality and temporal paradoxes. Unlike science fiction time machines that can travel backward in time and potentially create causal loops, gravitational time machines only enable forward time travel, preserving causality while still creating complex temporal relationships. A gravitational time traveler returning from a journey would arrive in a future they could not have influenced during their absence, maintaining logical consistency while enabling dramatic temporal displacement. The social and economic implications of gravitational time travel technology would be transformative. Individuals could potentially extend their lifespans by spending portions of their lives in high time dilation environments, effectively aging more slowly than the general population. Investment strategies could exploit time dilation effects by placing resources in temporal trust funds that appreciate over extended periods while investors age slowly in gravitational time machines. Scientific research could benefit enormously from gravitational time machine capabilities. Long-duration experiments that require centuries or millennia of observation time could be completed within human lifespans by conducting them in high time dilation environments. Alternatively, researchers could use gravitational time travel to observe the long-term results of experiments by positioning themselves to age slowly, while their experiments proceed at normal rates in external environments. The exploration of cosmic phenomena could be revolutionized by gravitational time machine technology. Astronomers could position themselves to observe stellar evolution, galactic dynamics, or cosmological processes that normally require timeframes far exceeding human lifespans. By aging slowly in gravitational time wells while maintaining observation capabilities, researchers could witness cosmic events directly rather than inferring them from indirect evidence. The ethical implications of gravitational time travel raise complex questions about fairness, equality, and the distribution of temporal resources. If gravitational time machines become available, should access be regulated to prevent the creation of temporal inequalities, where some individuals age much more slowly than others? How would society adapt to citizens with vastly different personal timelines and aging rates? Legal frameworks would need fundamental revision to address the complications created by gravitational time travel. Contracts, property rights, and social obligations would all require modification to account for parties aging at different rates and experiencing different temporal flows. The concept of simultaneous events would need redefinition in a society where individuals routinely experience time at different rates. The potential for gravitational time machines to influence human evolution and development presents fascinating possibilities. Selective aging through controlled time dilation could enable individuals to witness and participate in historical processes normally confined to multiple human generations. Knowledge and wisdom could be preserved across extended time frames through individuals who age slowly while accumulating experience over centuries or millennia of external time. But the development of gravitational time machine technology raises fundamental questions about the nature of time itself and humanity as relationship to temporal flow. What would it mean to live in a society where time travel into the future becomes routine? How would human psychology and culture adapt to the possibility of dramatically different personal timelines? What are the ultimate limits of gravitational time manipulation, and what new possibilities might open as our understanding of space-time geometry continues to advance? Chapter 7. The GPS Revolution. The global positioning system represents the most successful practical application of gravitational time dilation in human history. A technology so dependent on Einstein's general relativity that it literally could not function without continuously correcting for the effects of mass on the flow of time. Every GPS-enabled device, from smartphone maps to precision agriculture systems to military navigation, operates as a practical demonstration that massive objects slow down time, making gravitational time dilation not an exotic theoretical curiosity, but an essential component of modern technological civilization. The fundamental principle of GPS operation depends on extremely precise time measurements to calculate position through triangulation from satellite signals. GPS satellites continuously broadcast their location and the exact time according to atomic clocks aboard each spacecraft. GPS receivers calculate their position by measuring how long radio signals take to travel from multiple satellites, using the speed of light and signal travel times to determine distances to each satellite and thereby triangulate the receiver's location. This ranging technique requires timing precision measured in nanoseconds because radio waves travel at the speed of light, approximately 300 million meters per second. A timing error of just 1 microsecond translates to a position error of about 300 meters, while timing errors of 1 nanosecond create position errors of approximately 30 centimeters. For GPS to achieve its designed accuracy of a few meters or better, satellite clocks and ground-based timing systems must maintain synchronization to within tens of nanoseconds across global distances. But GPS satellites orbit at altitudes of approximately 20,200 kilometers above Earth's surface, placing them in a significantly different gravitational environment than ground-based GPS receivers. At this orbital altitude, Earth's gravitational field is weaker than at the surface, causing time to flow faster aboard the satellites than at ground level. This gravitational time dilation effect causes satellite clocks to gain approximately 45 microseconds per day relative to identical clocks on Earth's surface. The special relativistic effects of orbital motion create an additional timing complication that partially compensates for gravitational time dilation. GPS satellites travel at orbital velocities of approximately 3.9 kilometers per second, causing their clocks to run slower than stationary clocks due to velocity-dependent time dilation predicted by special relativity. This kinematic time dilation causes satellite clocks to lose approximately 7 microseconds per day relative to ground clocks. The combined effect of gravitational time dilation speeding up satellite clocks and kinematic time dilation slowing down satellite clocks results in a net gain of approximately 38 microseconds per day for GPS satellite clocks relative to Earth-based timing systems. While this might seem like a tiny effect, it would accumulate rapidly to create position errors exceeding 10 kilometers within a single day if not corrected, making GPS completely useless for navigation purposes. The GPS system handles these relativistic effects through multiple correction mechanisms built into both the satellites and ground-based control systems. GPS satellite clocks are intentionally adjusted to run slightly slow before launch. compensated to account for the faster time flow they will experience in orbit. Additionally, the GPS navigation message includes correction terms that allow receivers to account for residual relativistic effects, orbital variations, and other timing discrepancies. The development of GPS required overcoming significant skepticism about the practical importance of relativistic effects in engineering applications. When GPS was initially designed in the 1970s, some engineers argued that relativistic corrections were unnecessary complications that added complexity without practical benefit. Only careful analysis and testing demonstrated that relativistic effects would indeed render GPS unusable without appropriate corrections. The successful operation of GPS has provided continuous experimental verification of general relativity as predictions about gravitational time dilation. Every GPS satellite serves as a precision experiment in gravitational physics, with the system's navigation accuracy serving as ongoing confirmation that Einstein's theories correctly describe how mass affects the flow of time. The billions of GPS position calculations performed daily around the world represent perhaps the most extensive test of general relativity ever conducted. Modern GPS systems achieve positioning accuracies that push the boundaries of relativistic measurement precision. Advanced GPS applications, including surveying, precision agriculture, and scientific research, require centimeter-level positioning accuracy that demands even more sophisticated relativistic corrections. These applications must account for additional effects, including Earth's gravitational field variations, atmospheric delays, and satellite orbit perturbations that create subtle modifications to relativistic timing corrections. The European Galileo navigation system, Russia's GLONASS, China's Beidou, and other global navigation satellite systems all face identical challenges with gravitational time dilation and implement similar relativistic correction mechanisms. The success of these independent systems provides multiple confirmations that gravitational time dilation operates exactly as predicted by general relativity, making satellite navigation a technology that literally depends on Einstein's insights about the relationship between mass and time. Regional navigation systems and satellite-based augmentation systems extend GPS capabilities while introducing additional relativistic considerations. The Wide Area Augmentation System, WAS, European Geostationary Navigation Overlay Service, EGNOS, and similar systems use geostationary satellites at much higher altitudes where gravitational time dilation effects are different from GPS satellites, requiring customized relativistic corrections for optimal performance. Future navigation systems will push relativistic effects to even greater precision. Next-generation GPS satellites incorporate optical clocks and improved atomic clock technology that could achieve timing precision, approaching parts in YP, making gravitational time dilation corrections essential at unprecedented levels of accuracy. These advanced timing systems will enable navigation accuracies measured in millimeters while serving as increasingly precise tests of gravitational physics. The commercial applications of GPS have created economic incentives for continuous improvement in relativistic modeling and correction techniques. Precision agriculture systems that guide autonomous farming equipment, autonomous vehicle navigation systems, and infrastructure monitoring applications all require GPS accuracies that demand sophisticated understanding of gravitational time dilation effects. The economic value of GPS-dependent technologies has created substantial investment in relativistic physics research with practical applications. Scientific applications of GPS extend far beyond navigation to include geodetic measurements that exploit gravitational time dilation for research purposes. GPS-based measurements of tectonic plate motion, earthquake monitoring, and atmospheric research all depend on timing precision that requires careful accounting for relativistic effects. These applications have transformed GPS from a navigation tool into a scientific instrument for studying Earth, its gravitational field, and its variations over time. The development of GPS timing technology has enabled applications that leverage gravitational time dilation for purposes beyond navigation. Financial trading systems use GPS timing synchronization for high-frequency trading, where microsecond timing advantages create competitive advantages. Power grid synchronization, telecommunications networks, and scientific experiment coordination all rely on GPS timing systems that must account for gravitational time dilation to maintain required precision. Military applications of GPS push relativistic correction requirements to extreme levels for weapons guidance, surveillance systems, and precision targeting applications, where accuracy requirements approach the fundamental limits of current technology. These applications often require custom relativistic modeling for specific mission profiles that may involve unusual orbital mechanics or non-standard gravitational environments. The study of GPS relativistic effects has contributed to fundamental physics research by providing a platform for testing general relativity under controlled conditions. Researchers have used GPS satellites to investigate gravitational redshift, test alternative theories of gravity, and search for violations of Einstein's predictions with unprecedented precision. The global GPS constellation represents a distributed laboratory for gravitational physics research that operates continuously around the world. Space-based navigation systems beyond Earth orbit will require even more sophisticated relativistic corrections as spacecraft travel between different planetary gravitational environments. Interplanetary navigation systems will need to account for the gravitational time dilation effects of multiple planets, moons, and the Sun simultaneously, creating complex relativistic modeling challenges for future space exploration missions. The success of GPS has demonstrated that gravitational time dilation is not merely an academic curiosity, but a fundamental physical phenomenon with enormous practical importance for modern technology. The system's operation provides daily confirmation that massive objects do indeed slow down time in precisely the manner predicted by Einstein's general relativity, making GPS a technology that literally could not exist without our understanding of how mass affects temporal flow. But the GPS revolution raises broader questions about humanity's growing dependence on technologies that require sophisticated understanding of relativistic physics. What other applications might emerge as our ability to measure and control gravitational time dilation continues to advance? How will society adapt as more technologies require precise accounting for the effects of mass on time? What new possibilities might open as we develop even more precise control over gravitational timing effects? Chapter 8. Cosmic Clocks. Throughout the cosmos, countless natural processes serve as gravitational clocks, their rhythms modified by the massive objects around them in ways that reveal the true structure of space-time on astronomical scales. Pulsars emit precisely timed radio beams that slow down in strong gravitational fields. Binary star systems orbit with periods affected by gravitational time dilation. And even the expansion of the universe itself operates according to cosmic time that flows differently in various gravitational environments. Understanding these cosmic timekeepers transforms astronomy from a science of spatial measurement into a science of temporal cartography, mapping the flow of time throughout the universe. Pulsars represent perhaps the most precise cosmic clocks available for studying gravitational time dilation on astronomical scales. These rapidly rotating neutron stars emit beams of electromagnetic radiation that sweep across space like lighthouse beams, creating pulses that arrive at Earth with extraordinary regularity. The most stable pulsars maintain timing precision comparable to atomic clocks, with pulse arrival times predictable to within microseconds across years of observation. The pulse timing of pulsars provides direct measurements of gravitational time dilation in their immediate environments and along the paths their signals travel through space. Pulsars and binary systems with massive companions exhibit systematic changes in pulse timing as they orbit through varying gravitational fields, confirming Einstein's predictions for gravitational time dilation in strong field environments. The famous binary pulsar PSR B1913+16 demonstrated gravitational time dilation effects while also providing the first indirect evidence for gravitational wave emission. Double pulsar systems, where both neutron stars in a binary pair emit detectable radio pulses, create natural laboratories for testing gravitational time dilation with unprecedented precision. These systems allow astronomers to compare clocks embedded in the same gravitational environment while also observing how their signals are affected by the gravitational fields they encounter during orbital motion. Such measurements have confirmed general relativity's predictions for gravitational time dilation to extraordinary accuracy. The galactic distribution of pulsars creates opportunities to map gravitational time dilation throughout the Milky Way galaxy. Pulsars located at different distances from the galactic center experience different gravitational environments due to the varying density of matter in galactic structures. Systematic timing observations of pulsar populations could potentially reveal how gravitational time dilation varies throughout galactic gravitational fields, providing insights into dark matter distribution and galactic dynamics. Gravitational microlensing events provide another window into cosmic gravitational time dilation effects. When massive objects pass between Earth and distant stars, their gravitational fields bend and focus starlight, creating characteristic brightening patterns that depend on the geometry of the lensing system. These events also create gravitational time dilation effects that subtly modify the timing of variable star pulsations and other periodic phenomena in background sources. The cosmic microwave background radiation, the afterglow of the Big Bang, carries information about gravitational time dilation in the early universe. Temperature fluctuations in this primordial radiation encode information about density variations that created gravitational time dilation gradients during the universe's youth. Analysis of these patterns provides insights into how time flowed differently in various regions during cosmic evolution, revealing the temporal structure of the early universe. Active galactic nuclei powered by supermassive black holes create some of the most extreme cosmic gravitational time dilation environments accessible to observation. Matter falling into these black holes emits X-rays and gamma rays with characteristic timing patterns that reflect the gravitational time dilation experienced in the intense fields near event horizons. These observations provide direct evidence for the extreme time dilation effects predicted near black holes. Gamma ray bursts, among the most energetic phenomena in the universe, create brief but intense gravitational time dilation environments during their explosive events. The enormous energy densities achieved during these bursts approach levels where space-time curvature becomes significant, potentially creating measurable gravitational time dilation effects even at cosmological distances. Advanced timing analysis of gamma-ray burst signals might reveal signatures of these extreme gravitational environments. Gravitational wave astronomy has opened entirely new possibilities for studying cosmic gravitational time dilation. The LIGO and Virgo gravitational wave detectors observe ripples in spacetime itself created by accelerating masses, providing direct measurements of spacetime curvature where extreme gravitational time dilation operates. The signals from merging black holes and neutron stars carry information about time dilation effects in regions of spacetime curvature impossible to study by other means. Binary black hole systems detected through gravitational waves provide laboratories for studying gravitational time dilation in the most extreme environments accessible to current technology. As these systems spiral toward merger, The component black holes experience increasingly strong mutual gravitational fields that create dramatic time dilation effects. Analysis of gravitational wave signals reveals how time flows in these extreme environments, while testing general relativity's predictions in previously inaccessible regimes. The expansion of the universe itself operates according to cosmic time that flows differently in various gravitational environments throughout space. Regions with higher matter density experience slower cosmic time compared to regions with lower density, creating variations in the apparent rate of cosmic expansion when viewed from different gravitational environments. This effect must be accounted for when using distant supernova and other cosmic distance indicators to measure cosmological parameters. Dark matter and dark energy influence cosmic gravitational time dilation in ways that might be detectable through precision timing observations. If dark matter consists of massive particles that cluster gravitationally, it would create gravitational time dilation effects that could be mapped through pulsar timing or other precision astronomical observations. Similarly, dark energy's influence on cosmic expansion might create temporal effects detectable through careful analysis of cosmic clock systems. The search for gravitational waves from cosmic string networks, topological defects that might have formed during cosmic phase transitions, relies partly on understanding how these hypothetical objects would affect gravitational time dilation in their vicinity. Cosmic strings would create distinctive spacetime curvature patterns that influence the flow of time along their lengths, potentially creating detectable signatures in pulsar timing observations. Primordial black holes, if they exist, would create localized regions of strong gravitational time dilation that could influence cosmic evolution in subtle but potentially detectable ways. Pulsar timing arrays and other precision timing observations might reveal signatures of primordial black hole populations through their cumulative effects on the propagation of electromagnetic signals across cosmic distances. The development of space-based gravitational wave detectors like the proposed Laser Interferometer Space Antenna, LISA, will enable observations of gravitational time dilation in previously inaccessible cosmic environments. These instruments will detect gravitational waves from massive black hole mergers, extreme mass ratio in spirals, and other exotic systems that create intense gravitational time dilation effects throughout cosmic history. Future astronomical surveys using next-generation telescopes will map gravitational time dilation throughout the observable universe through precision timing observations of various cosmic phenomena. The Square Kilometer Array Radio Telescope will enable pulsar timing measurements with unprecedented precision, while optical and infrared surveys will provide timing measurements of variable stars, supernova, and other phenomena that serve as cosmic clocks. The study of cosmic gravitational time dilation also provides insights into fundamental physics beyond general relativity. Alternative theories of gravity often predict different relationships between mass and time dilation, making precision cosmic timing observations powerful tests of our understanding of gravitational physics. Deviations from Einstein's predictions in cosmic timing measurements could reveal new physics operating on astronomical scales. The practical applications of cosmic gravitational time dilation extend to navigation and timekeeping for future space exploration. Interstellar spacecraft will need to account for gravitational time dilation effects when navigating between star systems with different gravitational environments. Deep space missions will require timing systems that remain accurate despite traveling through varying gravitational fields over extended periods. But the study of cosmic clocks and universal time raises fundamental questions about the nature of time itself on cosmic scales. How do we define universal time in a universe where time flows at different rates in different gravitational environments? What does simultaneity mean for events occurring in distant galaxies with different gravitational time dilation? How do we understand cosmic evolution when the rate of that evolution depends on gravitational environment throughout the universe. Chapter 9. Quantum Gravity and Time. At the intersection of quantum mechanics and general relativity lies one of physics' greatest unsolved mysteries. How does gravitational time dilation operate at the quantum scale, where space and time themselves might be quantized into discrete, indivisible units? The emerging field of quantum gravity suggests that our understanding of how massive objects slow down time might be fundamentally incomplete, with quantum effects creating temporal phenomena that transcend classical general relativity and potentially offer new mechanisms for controlling and manipulating the flow of time itself. Quantum mechanics and general relativity, the two pillars of modern physics, provide seemingly incompatible descriptions of time at their respective scales. Quantum mechanics treats time as a universal parameter that flows uniformly throughout the universe, serving as the stage on which quantum processes unfold according to the Schrödinger equation. General relativity treats time as a dynamic dimension that can be curved, stretched, and modified by matter and energy, with no universal time coordinate that applies throughout spacetime. This fundamental incompatibility becomes critical at the Planck scale, approximately 10 to 35 meters and y-43 seconds, where quantum effects and gravitational effects become comparable in strength. At these scales, the very concepts of smooth spacetime and continuous time flow that underlie general relativity might break down, replaced by a quantized foam of discrete spacetime units, where time itself exists only in minimum increments. String theory, one approach to quantum gravity, suggests that the fundamental constituents of reality are not point particles, but extended objects, vibrating strings, and higher dimensional membranes that exist in 10 or 11 dimensions of spacetime. In string theory, gravitational time dilation emerges from the geometry of these extra dimensions, with massive objects creating curvature that affects the vibrational modes of strings in ways that modify the flow of time. The implications of string theory for gravitational time dilation are profound. If spacetime possesses additional dimensions beyond our familiar four, then massive objects might influence time flow through mechanisms involving the compact extra dimensions, potentially creating time dilation effects that differ from general relativity's predictions. These deviations might be detectable through ultra-precise measurements of gravitational time dilation in extreme environments. Loop quantum gravity, an alternative approach to quantum gravity, proposes that spacetime itself is quantized into discrete loops and networks at the Planck scale. In this framework, gravitational time dilation emerges from the statistical properties of these quantum spacetime networks, with massive objects creating patterns in the quantum geometry that modify temporal flow. Time becomes an emergent property of more fundamental quantum geometric relationships. The quantization of time suggested by loop quantum gravity implies that there might be a minimum possible time interval, a quantum of time analogous to the quantum of energy discovered by Max Planck. If time is indeed quantized, then gravitational time dilation would operate through discrete jumps rather than smooth variations, potentially creating detectable signatures in ultra-precise timing measurements. Causal set theory proposes that spacetime consists of discrete events connected by causal relationships, with both space and time emerging from the statistical properties of these fundamental causal structures. In this approach, gravitational time dilation results from changes in the density and connectivity of causal relationships in regions with different matter distributions. Massive objects create regions where causal connections become more sparse, effectively slowing down the flow of time. Emergent gravity theory suggests that gravitational effects, including time dilation, might not be fundamental features of spacetime, but rather emergent phenomena arising from more basic quantum mechanical processes. In these theories, gravity and gravitational time dilation emerge from quantum entanglement networks that connect matter throughout the universe, with massive objects creating patterns in quantum entanglement that manifest as classical gravitational effects. The relationship between quantum mechanics and gravitational time dilation becomes particularly intriguing when considering quantum clocks, theoretical quantum systems that could measure time with precision approaching fundamental quantum limits. These quantum clocks would be sensitive to gravitational time dilation effects at the quantum scale, potentially revealing how quantum mechanics and general relativity interact in previously unexplored regimes. Quantum superposition in gravitational fields creates paradoxes that challenge our understanding of both quantum mechanics and time dilation. If a quantum system exists in a superposition of states at different locations in a gravitational field, does it experience a superposition of different time dilation rates? How does quantum measurement collapse this temporal superposition? And what does this reveal about the relationship between consciousness, measurement, and the flow of time? Recent proposals for testing quantum gravity effects include experiments with atomic clocks in quantum superposition states, where the same clock system exists in a quantum superposition of different gravitational environments. These experiments might reveal whether gravitational time dilation operates differently for quantum systems in superposition compared to classical systems with definite positions. The Casimir effect, where quantum vacuum fluctuations create measurable forces between closely spaced conducting plates, might also involve gravitational time dilation effects at the quantum scale. The energy density of quantum vacuum fluctuations could create tiny but measurable spacetime curvature that influences local time flow, providing a laboratory technique for studying quantum gravitational time dilation effects. Black hole information paradox resolution might require understanding how quantum effects modify gravitational time dilation near event horizons. Recent proposals suggest that quantum entanglement between matter falling into black holes and the Hawking radiation they emit might create modifications to classical time dilation that allow information to escape from black holes through quantum mechanical mechanisms. The holographic principle, which suggests that all information in a volume of space can be encoded on its two-dimensional boundary, implies that gravitational time dilation might be fundamentally related to information processing rates on these holographic boundaries. This connection between information, quantum mechanics, and gravitational time dilation might reveal deep relationships between computation, consciousness, and temporal flow. Quantum error correction in gravitational systems might provide mechanisms for protecting quantum information from the decoherence effects typically associated with strong gravitational fields and extreme time dilation. If quantum information can be preserved through gravitational time dilation transitions, this might enable quantum technologies that operate efficiently in extreme gravitational environments. The measurement of quantum gravitational time dilation effects requires developing new experimental techniques that combine the precision of atomic clocks with the sensitivity of quantum measurement systems. Proposed experiments include quantum interferometry with matter waves in gravitational fields, precision tests of quantum mechanics in curved spacetime, and searches for discrete signatures of quantized time. Space-based quantum gravity experiments might provide the most sensitive tests of quantum gravitational time dilation effects. Satellites equipped with quantum sensors and atomic clocks could detect deviations from classical general relativity that reveal the quantum nature of gravitational time dilation, while also testing proposed quantum gravity theories through precision measurements of spacetime geometry. The implications of quantum gravity for controlling gravitational time dilation are potentially revolutionary. If time dilation emerges from quantum mechanical processes, then quantum technologies might eventually enable direct manipulation of temporal flow through quantum field control, quantum geometry engineering, or other quantum mechanical mechanisms. This could transform gravitational time machines from passive systems that exploit existing gravitational fields into active systems that create controlled time dilation environments. The relationship between consciousness and quantum gravitational time dilation raises profound questions about the nature of awareness in quantum mechanical systems. If consciousness involves quantum processes, as some theories suggest, then the experience of time might be fundamentally connected to quantum gravitational effects in ways that make subjective temporal experience sensitive to spacetime curvature at the quantum scale. But exploring quantum gravity and time raises the deepest questions about the fundamental nature of temporal existence. If time is quantized and emerges from more basic quantum geometric relationships, what does this mean for our experience of temporal flow? How do quantum effects modify our understanding of causality, sequence, and the arrow of time? What new possibilities for temporal manipulation might emerge as we develop technologies based on quantum gravitational effects? Chapter 10. Engineering Time. The prospect of deliberately manipulating gravitational time dilation through advanced engineering represents one of the most audacious possibilities in theoretical physics. The potential to construct artificial gravitational fields, control temporal flow with technological precision, and ultimately master time itself through carefully designed spacetime geometries. While current technology falls far short of such capabilities, the underlying physics suggests pathways toward temporal engineering that could transform human civilization's relationship with time from passive experience to active control. The foundation for engineering gravitational time dilation lies in the understanding that spacetime curvature, and therefore temporal flow, can be controlled through the distribution of mass and energy. Einstein's field equations demonstrate that matter and energy determine spacetime geometry through precise mathematical relationships, suggesting that sufficiently advanced civilizations might engineer spacetime curvature through artificial mass-energy configurations designed to create specific temporal environments. The energy requirements for significant artificial gravitational time dilation are staggering by current standards, creating gravitational time dilation comparable to that found near neutron stars would require concentrating enormous masses into relatively small volumes, demanding energy manipulation capabilities far beyond current technology. However, the fundamental physics imposes no absolute prohibitions on such engineering projects, only practical limitations that advanced civilizations might eventually overcome. Rotating massive objects offer one approach to engineering enhanced gravitational time dilation through frame dragging effects. The lens-throwing effect, where rotating masses drag spacetime around with them, creates additional time dilation beyond that produced by static gravitational fields. Artificial rotating systems with extremely high mass and angular momentum could potentially create significant frame dragging effects that enhance local time dilation. Exotic matter configurations might enable more efficient approaches to temporal engineering. Theoretical proposals include arrangements of negative mass or negative energy density that could create closed time-like curves, wormholes, or other exotic spacetime geometries. While exotic matter has never been observed directly, quantum field theory predicts its existence under certain circumstances, particularly near black hole event horizons and in regions with strong electromagnetic fields. The Alcubierre drive concept, proposed by physicist Miguel Alcubierre, demonstrates how exotic matter might be used to engineer spacetime geometry for practical applications. This theoretical propulsion system would contract spacetime ahead of a spacecraft while expanding spacetime behind it, potentially enabling faster-than-light travel without violating relativity. The same exotic matter requirements might be adapted for temporal engineering applications. Metamaterials, artificially structured materials with properties not found in nature, might provide approaches to controlling electromagnetic and gravitational fields in ways that influence local time flow. Theoretical proposals suggest that electromagnetic metamaterials could potentially influence spacetime geometry through their interaction with quantum vacuum fluctuations, creating small but measurable modifications to gravitational time dilation. Superconducting magnetic field systems might offer more practical approaches to temporal engineering through their effects on quantum vacuum structure. Extremely strong magnetic fields can modify quantum vacuum fluctuations in ways that potentially influence local spacetime geometry. While these effects would be tiny compared to gravitational time dilation from massive objects, they might represent achievable first steps toward technological control of temporal flow. Quantum field manipulation might provide the most promising pathways toward practical temporal engineering. If gravitational time dilation emerges from quantum mechanical processes, as suggested by quantum gravity theories, then quantum technologies might enable direct control of temporal flow through quantum field engineering. This could include manipulation of quantum vacuum energy density, control of quantum entanglement networks, or engineering of quantum spacetime geometry. The Casimir effect demonstrates that quantum vacuum fluctuations can create measurable forces and energy densities that might influence spacetime curvature. Advanced techniques for manipulating Casimir energy could potentially create controlled modifications to local gravitational fields and their associated time dilation effects. While current Casimir manipulations produce tiny effects, scaling up these techniques might enable significant temporal control. Laser-driven approaches to temporal engineering might exploit the relationship between electromagnetic energy density and spacetime curvature. Ultra-high-intensity laser pulses can create energy densities approaching those required for measurable gravitational effects. Future laser technologies might enable creation of controlled electromagnetic field configurations that produce artificial gravitational time dilation through pure energy density effects. Plasma physics approaches might utilize controlled fusion or antimatter reactions to create the energy densities needed for significant spacetime curvature. Magnetic confinement fusion systems or antimatter storage systems could potentially concentrate energy in ways that create measurable gravitational time dilation, while also providing the power sources needed for advanced temporal engineering systems. Nanotechnology and molecular engineering might enable construction of materials and devices capable of creating artificial gravitational fields through precisely controlled mass distributions. Programmable matter systems could potentially reconfigure themselves to create desired gravitational field geometries, while molecular scale engineering might enable construction of materials with exotic properties suitable for temporal engineering applications. Space-based temporal engineering projects might offer advantages over terrestrial approaches through access to vacuum environments, unlimited construction space, and freedom from planetary gravitational constraints. Orbital or interstellar construction projects could potentially create artificial gravitational systems large enough to produce significant time dilation effects without the engineering constraints imposed by planetary surface conditions. Asteroid belt mining and space-based manufacturing could provide the raw materials needed for large-scale temporal engineering projects. Converting asteroid matter into precisely configured mass distributions might enable construction of artificial temporal environments without requiring exotic matter or extreme energy densities. Such projects might represent the first practical steps toward technological control of time flow. The development of temporal engineering capabilities would require advancing multiple scientific and technological frontiers simultaneously. Progress in quantum gravity theory, exotic matter physics, energy storage and manipulation, advanced material science, and space-based construction would all contribute to eventual temporal engineering capabilities. The convergence of these research areas might enable breakthrough advances that make temporal control achievable. Safety considerations for temporal engineering projects would be paramount, as uncontrolled spacetime manipulation could create dangerous gravitational fields causality violations, or other hazardous effects. Temporal engineering systems would require sophisticated safety mechanisms, fail-safe designs, and careful isolation from populated areas to prevent accidental harm from gravitational field anomalies. The applications of controlled gravitational time dilation extend far beyond scientific research to include medical applications, industrial processes, and social technologies. Controlled temporal environments could enable extended lifespans through biological aging rate control, accelerated manufacturing processes through differential time flow, and enhanced computational capabilities through temporal parallelism. Medical applications might include temporal therapy systems where patients experience controlled aging rates for treatment of various conditions, rehabilitation environments with optimized temporal flow for recovery processes, and life extension technologies that enable individuals to age more slowly through technological rather than biological interventions. Industrial applications could include temporal manufacturing systems, where complex processes occur in accelerated or decelerated time environments, quality control systems that utilize differential aging for materials testing, and research facilities where long-duration experiments proceed rapidly through temporal acceleration techniques. But engineering time raises fundamental questions about the ethics and consequences of temporal manipulation. Who should control temporal engineering technologies? How do we prevent temporal manipulation from creating social inequalities or disrupting natural temporal relationships? What are the ultimate limits and risks of technological control over the flow of time itself? Chapter 11. Temporal Reality. The discovery that massive objects slow down time around them forces us to confront the most fundamental questions about the nature of existence itself. What is time? How does our consciousness relate to temporal flow? What does it mean for reality to exist when time itself is malleable, relative, and dependent on gravitational environment? These questions extend far beyond physics into philosophy, consciousness studies, and our understanding of what it means to be aware beings existing within a universe where time is not universal but local, not absolute but contingent on mass and energy. The classical understanding of time, inherited from Newton and common sense, treated temporal flow as universal and absolute, a cosmic clockwork that ticks at the same rate everywhere, providing a universal standard of now that applies throughout the universe. In this view, time serves as a passive stage where events unfold, with past, present, and future having objective reality independent of observers. This intuitive picture seems so obviously correct that questioning it appeared philosophically absurd. But gravitational time dilation shatters this intuitive framework completely. If time flows at different rates in different gravitational environments, then there is no universal now that applies throughout space. Events that appear simultaneous to one observer will be sequential to another observer in a different gravitational field. The past, present, and future become relative concepts that depend on gravitational environment rather than objective features of reality. This relativity of simultaneity creates profound philosophical puzzles about the nature of existence and identity. If time flows differently in different locations, what does it mean for events to be real? When we say something exists now, we implicitly assume a universal present moment. But gravitational time dilation reveals that now is a local concept that has no meaning beyond specific gravitational environments. The block universe interpretation of spacetime treats all moments in time as equally real, with past, present, and future existing simultaneously in four-dimensional spacetime. From this perspective, gravitational time dilation doesn't create temporal paradoxes because all moments exist eternally within the spacetime manifold. Your past and future selves are as real as your present self, existing at different locations in spacetime, just as your body extends through different locations in space. But the block universe interpretation raises disturbing questions about free will, causality, and the meaning of choice. If all moments exist simultaneously in spacetime, then your future decisions already exist as real events within the block universe structure. Gravitational time dilation becomes a way of navigating through this eternal block rather than participating in the creation of genuinely new moments. Alternative interpretations of temporal reality attempt to preserve the objective flow of time while accounting for gravitational time dilation effects. The presentist interpretation maintains that only the present moment is real, but it must explain how present can be defined consistently across different gravitational environments. This leads to proposals for preferred reference frames or universal time coordinates that maintain objective temporal flow despite local gravitational variations. The growing block theory represents a compromise position where past and present moments are real, but future moments don't yet exist. This interpretation must explain how the boundary between existing and non-existing moments behaves in the presence of gravitational time dilation, potentially requiring complex rules about how temporal reality unfolds differently in different gravitational environments. Consciousness-based theories of time propose that temporal flow emerges from the information processing activities of conscious observers, rather than being a fundamental feature of physical reality. In this view, gravitational time dilation affects consciousness by modifying the rate at which conscious beings process information, creating subjective experiences of altered temporal flow while preserving the objective reality of conscious experience itself. The relationship between consciousness and gravitational time dilation raises profound questions about the nature of awareness in curved spacetime. If consciousness depends on neural processes that operate according to biological timescales, how does gravitational time dilation affect the subjective experience of thought, memory, and decision-making? Would consciousness feel sluggish in strong gravitational fields? Or would subjective experience automatically adjust to maintain normal awareness regardless of external time flow? Some theories propose that consciousness might be fundamentally connected to the structure of spacetime itself, with awareness emerging from quantum mechanical processes that couple directly to gravitational fields. If consciousness is indeed sensitive to spacetime curvature, then gravitational time dilation might affect not just the rate of conscious processing, but the very nature of conscious experience, potentially altering perception, memory, and the subjective sense of temporal flow. The many worlds interpretation of quantum mechanics interacts with gravitational time dilation in complex ways that challenge our understanding of both quantum reality and temporal experience. If every quantum measurement creates branching realities where all possible outcomes occur, then gravitational time dilation might affect the rate at which these quantum branches proliferate, creating temporal landscapes where the structure of quantum reality depends on gravitational environment. The anthropic principle suggests that we observe the particular physical constants and gravitational conditions that we do because they permit the existence of observers like ourselves. In the context of gravitational time dilation, this might explain why our cosmic environment has gravitational conditions that allow for stable biological timescales and coherent conscious experience across reasonable spatial scales. Temporal experience becomes particularly mysterious when considering extreme gravitational environments where time dilation approaches infinite values. What would consciousness be like for a being that could somehow survive near a black hole event horizon, where time appears to stop from external perspectives? Would such a being experience normal temporal flow from their own reference frame? Or would consciousness itself be fundamentally altered by extreme spacetime curvature? The possibility of artificial temporal environments created through gravitational engineering raises ethical questions about the manipulation of conscious experience through technological control of time flow. Should there be limits on how dramatically temporal flow can be altered artificially? What rights do conscious beings have to experience natural temporal environments versus technologically modified ones? Digital consciousness and artificial intelligence face unique challenges in gravitational time dilation environments. If consciousness can be implemented in artificial computational substrates, how do these systems maintain coherent temporal experience when operating in variable gravitational fields? Would artificial consciousness automatically adapt to different temporal environments? Or would it require specific programming to handle gravitational time dilation effects? The preservation of consciousness across extreme gravitational transitions might require developing new technologies for maintaining coherent awareness while traversing regions with dramatically different time flow rates. This could include artificial memory systems that maintain continuity of experience, temporal synchronization technologies that coordinate consciousness across different gravitational environments, or even forms of consciousness transfer that enable awareness to adapt to varying temporal conditions. The ultimate questions raised by gravitational time dilation extend to the purpose and meaning of existence in a universe where time itself is not fundamental, but emerges from the relationship between matter, energy, and space-time geometry. If time is malleable and controllable through gravitational engineering, what does this reveal about the nature of reality and our place within it? The possibility that time travel into the future is achievable through gravitational time dilation creates profound philosophical questions about identity, continuity, and the meaning of personal existence. If you could use gravitational time machines to travel centuries or millennia into the future, would you remain the same person despite the vast temporal displacement? How would consciousness maintain continuity across such extreme temporal journeys? The implications for mortality and the meaning of life become particularly profound when considering gravitational time dilation as a form of life extension. If biological aging can be slowed through positioning in strong gravitational fields, does this represent genuine life extension or merely a different way of experiencing the same finite lifespan? How do we understand the value and meaning of life when its duration becomes dependent on gravitational environment? The study of gravitational time dilation might ultimately reveal that time itself is not the fundamental feature of reality we intuitively believe it to be, but rather an emergent property of more basic relationships between consciousness, information, and space-time geometry. This could transform our understanding of existence from temporal beings experiencing flow through time to conscious patterns embedded in the eternal mathematical structure of space-time itself. But contemplating the philosophy of temporal reality in a universe where time is controlled by massive objects raises the deepest questions about existence, meaning, and our cosmic destiny. What does it mean to be conscious in a universe where time is flexible? How do we find purpose and meaning when temporal experience itself can be technologically controlled? What is the ultimate nature of the reality we inhabit when even time itself proves to be relative, malleable, and dependent on the gravitational environment in which consciousness finds itself embedded? Throughout this exploration of how massive objects steal time, we've uncovered one of the most profound truths about reality. Time is not the unchanging universal constant we intuitively believe it to be, but a dynamic, malleable dimension that bends to the will of mass and energy throughout the cosmos. Every massive object in the universe, from the Earth beneath your feet to the supermassive black holes at galactic centers, is continuously reshaping the flow of time itself, creating a cosmic landscape where temporal experience depends entirely on your position in the gravitational fields that permeate spacetime. We've seen how Einstein's general relativity revealed time and space as unified into a four-dimensional fabric that curves in response to matter and energy, making gravitational time dilation not an exotic correction to classical physics, but a fundamental feature of existence itself. The mathematics are precise and unforgiving. The stronger the gravitational field, the slower time flows, with effects that range from the microscopic, detectable only with atomic clocks across centimeter height differences, to the cosmic, where time near black holes can slow to virtual standstill compared to distant observers. The experimental evidence has evolved from subtle confirmations to routine technological dependencies. GPS satellites must continuously correct for gravitational time dilation to maintain navigation accuracy, making every smartphone location a practical demonstration that massive objects slow down time. Atomic clocks now detect these temporal effects across height differences smaller than a grain of rice, while observations of pulsars and gravitational waves reveal time dilation operating in the most extreme environments accessible to human observation. But perhaps the most profound realization is how deeply gravitational time dilation affects every aspect of existence. Your biological rhythms, aging processes, and potentially your consciousness itself operate within time streams that are constantly being modified by every massive object in your environment. You don't just live in space, you live in space-time, and that space-time is being continuously sculptured by gravity in ways that shape your temporal experience at every moment. The cosmic implications transform our understanding of time travel from science fiction fantasy to scientific inevitability. Gravitational time machines don't require exotic matter or speculative physics. They operate according to well-established general relativity, requiring only the ability to position yourself in strong gravitational fields and return to weaker fields after experiencing differential aging. Every black hole becomes a gateway to the future. Every neutron star a natural time machine where minutes can become years. The frontiers of quantum gravity suggest that our understanding of gravitational time dilation might still be incomplete, with quantum effects potentially offering new mechanisms for temporal control that transcend classical general relativity. If time emerges from more fundamental quantum geometric relationships, then quantum technologies might eventually enable direct manipulation of temporal flow through mechanisms we're only beginning to imagine. The engineering possibilities stretch towards science fiction, but rest on solid physics foundations. Advanced civilizations might learn to create artificial gravitational fields that control time, flow with technological precision, enabling temporal environments optimized for specific applications. From medical therapy through controlled aging rates to manufacturing processes that exploit differential time flow for enhanced efficiency. As you continue living after contemplating these temporal mysteries, remember that your very existence unfolds within a cosmic clockwork where massive objects continuously steal time from everything around them. When you climb stairs, you're moving between regions where time flows at slightly different rates. When you look up at the stars, you're seeing light that has traveled through gravitational time dilation fields that have subtly affected its journey across space. The Earth's gravitational field is aging your feet slightly slower than your head. The Sun's massive presence is slowing down time throughout the entire solar system. The supermassive black hole at our galaxy's center is creating temporal effects that influence the flow of time for our entire cosmic neighborhood. You exist within nested hierarchies of gravitational time dilation that shape your temporal experience in ways so subtle they're normally imperceptible, but so fundamental they affect every aspect of physical reality. This cosmic perspective dissolves the intuitive boundary between yourself and the universe's gravitational architecture. You are not separate from the massive objects that control time. You are embedded within their temporal influence, participating in a cosmic dance where matter, energy, space, and time interact to create the four-dimensional stage where consciousness experiences existence. The future of humanity might depend on learning to navigate not just through space, but through time itself, mastering gravitational time dilation as we venture into cosmic environments where temporal effects become dramatic. Space colonization becomes temporal colonization as we adapt to life in gravitational environments where aging rates, biological rhythms, and potentially consciousness itself operate according to temporal landscapes shaped by massive objects throughout the cosmos. If you found yourself fascinated by the discovery that time itself is under the control of massive objects, that your personal timeline is continuously being modified by gravitational fields, and that the universe contains natural time machines scattered throughout space, subscribe and give this video a thumbs up. Explore my investigation of the nature of space-time itself, where we delve even deeper into how the fabric of reality bends, twists, and responds to matter and energy in ways that challenge every intuitive notion about existence. The universe has revealed one of its most profound secrets. Massive objects don't just attract other matter through gravitational force. They steal time itself, bending the very flow of existence to their gravitational will. In a cosmos where time is flexible, your existence becomes both deeply personal and utterly cosmic. As your consciousness experiences temporal flow shaped by the massive objects that dominate the gravitational architecture of space-time. Time is not universal, not absolute, not the unchanging metronome of cosmic evolution. Time is local, relative, and malleable, shaped by mass and energy in ways that make every massive object a temporal sculptor, carving the flow of existence into patterns that reveal the deepest connections between matter, energy, space, time, and consciousness itself. The massive objects around you are stealing time every moment, and now you understand exactly how they do it.